Okay, so the next problem says find the quotient q of x and the remainder r in the division of 3x to a fifth minus 5x squared plus 2 by x minus 2. That term, or that expression, or that instruction is the same thing as saying evaluate this. 3x to a fifth minus 5x squared plus 2 divided by x minus 2. So what we need to use is long division of polynomials. So if this was an expression like 4 over 3, you could use long division normally, right? So this is how you would normally use long division. And you would say, oh, it goes into this once, and this is this, and I would subtract these two, and I would get 1, and I would put this here, and 3 goes into that exactly 3 times, so I get 1.3, yada, yada, yada. Same thing goes for long division of polynomials. The way that I usually write out the polynomial as it occurs in the numerator when put into here is the highest power first, and then the next lowest power. If it doesn't occur in the numerator, you should write it with a 0 coefficient, right? It's the same thing as when you have a numerator as a number. You wouldn't, if I had 4.01 divided by 3, you would not write 3 divided by 4.1 because these two are not equal to each other. So it's analogous to writing out all your decimal places, right? I have 3x to a fifth plus 0x to a fourth plus 0x to a third minus 5x squared plus 0x plus 2. If I want to find, I want to find what I have to multiply what I have to multiply x by to get 3x to a fifth. So 3x to a fourth will give me 3x to a fifth. So I take this and multiply it to x, and I get out 3x to a fifth. Let me erase this so we can still see that. Then you have to multiply it to your negative 2, and then this gives us negative 6x to a fourth. Subtract the terms that you can see here from the terms that you can see here. So 3x to a fifth minus 3x to a fifth is 0. And 0x to a fourth minus a negative 6x to a fourth gives me a plus 6x to a fourth. And then we would bring down whatever our next term is, 0x cubed, from what our numerator is. And then we go about the process again. We try to find what we have to multiply x by in order to get out a 6x to a fourth. So in order to get out a 6x to the fourth, when we multiply it by x, we need to multiply 6x to a third. Multiplied by x gives us, gives us 6x to a fourth. Let me erase all that stuff. Okay, so we continue this process all the way down. The polynomial that I got was 3x to a fourth plus 6x to a third plus 12x squared plus 19x plus 38. To check that, and part of what they say to do is to express that quotient, or the whole thing, as x minus 2 times the quotient function of x plus the remainder. So one thing that we can do is, when we write it out like that, is actually check it and see that we get back out the thing that we first put in as the numerator. So if I multiply x minus 2 to the expression that I just got, so I multiply x times 3x to a fourth, I get out x to a fifth. I multiply x to 6x to a third, I get out 6x to a fourth. x, and so I'm just increasing the power by 1 whenever I multiply to each one of these, right? So 12x squared becomes 12x cubed, 19x becomes 19x squared, 38 becomes 38x. Then I have to distribute the negative 2 to each one of these terms. So negative 2 times 3x to a fourth gives me negative 6x to a fourth. Negative 2 times 6x to a third gives me 12x to a third. And so on and so forth, right? And then we, so negative, all the way up to negative 2 times positive 38 gives us negative 76. So, sorry, I wanted to erase that. So, then we bring down our positive 78, right? I could have written this in one big long way, all the way down to here. I didn't do that so that I could see which terms easily combine with one another. So these terms cancel, these terms cancel. These terms combine and leave me with a negative 5x squared. These terms cancel, and the negative 76 and the positive 78 leave me with a plus 2. So I can see that what I put in as the numerator, right, I get back out when I multiply the quotient function that I just took, or just found, with the denominator. So I get out the thing that I was supposed to get in when I add the remainder in there. Okay, so therefore your final answer should be written in that form. Okay, release that. Okay, so next problem says to sketch x to a third over 2 plus 2x squared plus 3x. So this is an x cubed term. I know that x cubed terms either look like this or they look like this. They look like this when the coefficient of the cube term is positive, which it is. So I know in the end it will look something like that, right? I try to find my zeros, right? So if I factor out a x from this expression, because there is an x in each term, I have this expression, right? And this is 0 when x equals to 0, so that I know therefore that I have exactly one 0 of my function at x equal to 0. And then I have this expression, which is a quadratic, right? I looked at the discriminant real quick. I said, all right, well, my b is 2, my a is 1/2, my c is 3, and when I threw that in to b squared minus 4ac, I got out a negative 2. This tells me that this expression never equals 0. So therefore, if this never equals 0, I have only one 0, and that is at 0, at x equal to 0. So then I just found some numbers that were close to 0, and I plug and chug them in and generated a table, and then connected the dots with that table. And that's the answer that you see here. All right, let's do number 42. So number 42 says solve the equation negative 2x squared minus 6x plus 4. I just threw it into the quadratic formula, right? I also, if I set this equal to 0, I can multiply through by a negative 1, and I get out more positive coefficients than I have negative coefficients. I don't know why I like to do that. I just like to do that. So I have a equal to 2, b equal to 6, c equals to negative 4. Threw it into my discriminant, and I found 68, right? And I was trying to then decompose 68 into its prime factors. The reason that I did that was so that I could find the square root without having to use a calculator, right? So 68 is the same thing as 2 times 34, which is the same thing as 2 times 2 times 17. So if I found the square root of 68, it's the same thing as finding the square root of 2 times 17. I have here the square root really of 4, which we know is 2, but we can see that if I have 2 factors in here, which are the same, I can take them out of the square root, leaving me only with square root of 17. This allows me to write a more precise solution without having to rely on decimal places until maybe I get to the very end. So here I say I have -6 plus or minus b squared minus 4ac, which is the same thing as this, evaluated, divided by 2a, which is 4. And I let the terms in the numerator share this denominator of 4, and I get -3 over 2 plus or minus square root of 17 over 2. If I evaluate this as a decimal, then I get -1.5 plus or minus 2.06, which is square root of 17 divided by 2. And so here are my 2 zeros expressed as a decimal place. Also, this would have been acceptable, right? It says to find the zeros. It doesn't say to approximate it to any decimal places. I just do that just so that I can see it a little more clearly. All right, we'll start off on 43 in the next video.